Thank you and welcome. So we will discuss a little bit about some basics to make sure that we have the same vocabulary when we talk about models and parameters. Some high school maths we are going to touch this, and then we will look at model saving formats and model servers that are the enablers, the systems that help us serve models in production. We will, as SREs, we will look at some things around the deployment, the monitoring, and scaling techniques. I'm Theophilos. I'm working at Amazon as an engineer in European operations. My team is responsible for optimizing the fulfillment centers operations. When you buy something from Amazon.com, you get a promised delivery date, and we are making sure that we will deliver on that date. If something is going wrong, it's the KPI that we are tracking. And that's what we are trying to optimize across our fulfillment process. I'm a specialist in ML and Kubernetes. I'm active in the communities, in Kubeflow, in Kserve, and I love working with Python and Go. I live in Amsterdam. So let's look at some basics now. I'm using some simple plots here to just give you the vocabulary that we are going to use in the slides about the SRE, also to make people who are not comfortable with machine learning feel a little bit more comfortable. If I will have here the 4 people with their weight and their height, and I put them in a plane, and I will be able to build a model using a linear regression that is something that we have done in high school, and I can tell that if my weight is, let's say, 90 kilos, most probably my height is around 180. Yes? So this line is something that is also represented with a mathematical function, and it has 2 numbers. The one number is the slope of the line, and the other number is the intercept that will be, if we will put the 0 value in x, it will be the value that we will have in y. So to put the labels on this, the line is what we call the model, is our understanding of the world, is how would I position to answer the question, if my height, if my weight is 90 kilos, what is the expected height of me? Is 180, right? That's what the model is doing. And the 2 parameters that we have here are the slope and the intercept. Now, if I will position my 2 kids in that plot, and I will reuse the line that I have produced before, my understanding of the world with the 4 samples that I've got from my population is not quite good to predict the height of my sons. And that's because the kids have different development and growth process. So the model that I have built before, because it was very biased on a small data set of 4 people, it's not able to reflect correctly the world as it is in reality. So what usually data scientists are doing are retraining the model with new data that they have in their availability, and then we have a new line here with different new parameters, 0.9 for x and 92 for the intercept. So now this model is not good enough, though, to give accurate predictions, because we all know that it's not actually a linear model that is expressive enough to give the prediction that we are looking to make, which is to say, if your weight is this, your expected height should be that. So data scientists usually use more complex models, like a polynomial function that can have more than 2 parameters, like 3 parameters in that case. And it's more common to see such growth curves, as we call it, for children, and observe it as parents as they grow. And now the parameters have changed, and the parameters are 3. This is quite important for the talk, and that's why I'm presenting this. And if we go to a more complex and more expressive model, like a neural network, my function now is a dot product between an array of weights, as they are called, or parameters, and the x that I've got as input. So this example of a neural network with 1 million parameters is something that is in practice represented in an array of loads. Okay, that's all the math we got for today. So the model is the collection of the parameters, right? The model for the first function was 2 parameters, for the second is 3, etc. Now, my model might have 1 million parameters. So these are the variables or the weights of the neurons that have been trained, and we want to deploy it in production. The data scientist is throwing over the fence the model to our storage, and no DevOps, no MLOps world yet, and we have to take this model and deploy it to production. The model contains both the weights and the architecture of the network. And that architecture is nothing complex, it's just the Python, let's say, library or the Python class that will be instantiated to load these particular data types. So, and we know very good, at least some people who like Python know that there is a popular way to save Python data type data in the disk, and it's called pickle. It's a nice way to serialize your data together with a declaration on your on the class that it will evaluate when you will load this. Of course, that's not very safe to evaluate a class that you do not control. So it's not advisable to use and load and evaluate third-party job-lib or pickle dumps. If you see here on loading the model from pickle, you see here an array of 12 points. So that was a neural network with 10 inputs and a hidden layer in between with another 10 elements, another 10 neurons, and these are the weights of these neurons, and at the output it has 2 neurons, which is the one or the other class for the predictor that was dumped. So there are more complex and more expressive model file formats. From TensorFlow, we have the saved model that, together with the model architecture and the variables, it can also save some metadata about the model in order to be able to document it and track it in the machine learning pipeline. But this is not our area of focus today. Today is about serving. So there is a data file, like every database has a data file, and there is an index and a protobuf file that defines which are the neurons and which hidden layers are connected with the others. So this architecture is saved in the form of a protobuf file. I can load this file, I can inspect it, I can see the name of the keys of this array, which is essentially the name of the kernel, the name of the neuron, and the value has the floating point. Same story with another format. PyTorch has the PyTorch model archive. The same way we've been doing the WAR files in application deployment, we have now the MAR files, which is the model archive, and we can store it in a representation like this. The PTH file is the equivalent of the model file of TensorFlow. The difference is that it's using an order dictionary to store the keys. And a couple of model servers. There is TensorFlow serving, an optimized model server that is able to load the file from the disk, to load this protobuf file, to understand the architecture, load the weights from the disk, and then make it available through gRPC, through HTTP in order to serve requests. The same with PyTorch. It has a project called TorchServe that is making available a lot of workers to be able to receive throughput and answer questions on HTTP requests. Now, let's see how do we deploy it typically in scale. What we call inference in the space of machine learning is that what we typically have in the space of web APIs, where we send a question to the web server and we expect an answer. And the web server is having the weights loaded, right? The model. We send the question, I'm 100 kilos, and I'm expecting the server to reply to me, if it has the right W, to do the matrix multiplication between the X and the W, and give me back the answer Y, which is the 190, if my model was a neural net. All good so far? So it's important to repeat that we send the X, it's doing the matrix multiplication, and it's giving back the answer. There's nothing else fancy about machine learning serving. We need workloads that can do matrix multiplication between X and W. And this matrix multiplication is very specific. it cannot suddenly be more expensive than the previous request. It will always be between, I don't know, one number and another number, 1 million parameters and 100 inputs. It will always be the same and predictable. So when you are designing workloads for machine learning, for serving, you should expect that your workload will not be sudden according to the behavior of the application, or the behavior of the model. It will always be the same. It doesn't have I/O, it doesn't have connections external, it doesn't have any ways to manage threads. No, it's just a matrix multiplication between X and W. And preferably we do it on the GPU. Now, what about if I will ask the question, I'm 202 pounds because I'm from another region? The server will not be able to give me an answer because suddenly the input I'm giving is quite different. So in the space of machine learning, we have the concept of a transformer, and not to be confused with a typical model transformers. We have the concept of a transformer that will do just the simple transformation, the pounds to kilos, and vice versa. When it will receive the answer from the server, from the matrix multiplication, it will do the opposite transformation from kilos to feet and inches. So the vocabulary again, we have the concept of the transformer that is doing the pre and post transformation, and the model server itself is important to do the matrix multiplication and only that, nothing else. Now, as we build this deployment pipeline, or this deployment, we take the model outside of the server, we put it in a storage, we have a lot of servers running that are loading the model and serving it outside of the training process. So I believe the model file is the area where the world of the data scientist, the researcher is ending, and the world of the SRE or the operator starts. Of course, MLOps is attacking this area with the same principles that we have seen in our world. But this is just something to remember. The model file is where two worlds meet, if there are two worlds. To make it a little bit more complex, we take Kubernetes cluster, we put it in a couple of pods. We make sure that there is connectivity between the transformer and the model server. We want them to be in different pods because maybe the transformer is not that expensive and we can fit it in the CPU, and the pod of the model server can go to the GPU node. Yeah. And we build around it. We do put an envoy proxy to make sure that we have some mesh capabilities, to delegate the logging, the monitoring, the security, all these elements that we know and we need to a service mesh. And we have also the concept of the init container that we can have in the pod that will play the role of loading the model from the remote location and storing it in the disk to make it available for the model server. The same concept with the transformer. Maybe we can take out of the transformer the rules of the transformation and put them in a storage. This is something typical that is happening. In the world of NLP, in the world of natural language processing and language models, we call these transformations usually tokenization because it's just about getting a word and mapping it to a number. Actually, it looks like this. That would be these are the numbers for site reliability engineering from the most popular tokenizer. And we have already seen the model weights, how they look like. So these are the two files that we have in our storage. I will quickly go through the model monitoring because this is an SRE conference and it's important to talk about these service metrics. These are de facto. We all know, we all track this latency, success rate, number of invocations of our model. Maybe we have some dimensions in our Prometheus by model version or model itself. People like to use transaction monitoring to be able to see what is the latency that you have across different components in the application and be able to track and troubleshoot, is my transformer slow or is my predictor slow? Because when the model is increasing, the matrix multiplication might be more expensive than the transformer, but there are cases that the transformer is more expensive than the predictor, like loading a full language model tokenizer that is in the size of gigabytes. There is also the concept of explainer, but it's not we're not going to cover it here, but I'm mentioning it because as the pod or as the inference service in the cluster is becoming more complex, we have more components that are connecting with each other. And that's why, as part of our monitoring, we also need to have the kind of routing flow to be able to see how many of the requests are ending up to the predictor from the transformer and how many of the requests are going to the explainer, to be able to do this kind of monitoring with our nice visuals of Kiali in the STO service mesh. Prometheus metrics are exposed out of the box from the model servers. Typical metrics of the model server and not the model are the latency that it has in order to load the model in memory, to pick it up from the disk, to load it in the CPU memory, and then to copy it in the GPU memory. Some of the model servers can also do direct copy from the disk to the GPU memory by using, of course, as a bus, the CPU memory, but not waiting for the full file to be loaded from the one place to the other. Important metric is also the warm-up latency. So you can track it and you can declare it as a metric to know when your pod or your container is ready to serve traffic, right? So you can put it in the appropriate fields to listen, to look at it, and when it's ready to send the traffic. For logging, now here's the thing. After doing inference, and after predicting and saying for my weight, the expected height is this is new information that you have produced. And this is IP of your business, right? That all the efficiency that your data scientists have spent to build that model is in the model, reflected in the model itself, but also in the new data that you are producing. The new data is that for that weight, that's the height. Or for that particular person with this salary and this family, that's the loan that I need to give them. Because this mapping that you have done between X and Y is the treasure, and you need to treat it as, like we say, the first-class citizen in your operations, right? You need to store this not just as a log in a forgotten server. You need to put it in a bus, you need to put it in a broker, and then reuse it and start consuming it. You need more models downstream from this log to be able to do anomaly detection, to be able to do some drift detection and see what is happening. Do I have class imbalance? Am I suddenly predicting more of this other than that? And is it time for me to retrain? So you also need to have triggers that are monitoring these metrics, and when the appropriate metrics are reaching a threshold, maybe, you need to trigger the retraining job of your ML pipeline. So storing the outcome of the prediction is quite critical as the data used for training itself, right? Because you can also reuse this data for training. The new X that you have seen, so the new questions of the world, can be reused for rebuilding your models. Getting a little bit deeper on that, that's not for SREs, but maybe you will see these. It's important to know that in the concept of drift detection, the data scientists like to create some descriptive statistics about the data set. Let's say for some deliveries, we have, let's say for taxi drivers, this example, we have some fare, and this fare should be between 0 and 70. That's like the 700. That's the minimum and maximum value that I'm expecting this input to have in my inference request. So this is what we call a schema, and then that schema can be used versus the new version of the model to compare for any differences. And the TensorFlow data validation service is an excellent component that can offer this to us. Now, why I did add this component is because the data schema itself can also be reused by us, by SREs, in the transformer to validate the inputs as they are coming. Because if the ML pipeline has already executed the data validation to get the descriptive statistics of the input, I know that there is a schema file, a protobuf file most probably, that says this is the input that I'm expecting, and that input should be the mechanism that I will use as a validation. So if suddenly I will see that for a taxi delivery there was a payment of 1,000, this is an anomaly. I should not even, I should catch this exception. And that's it in the space of monitoring. On the world of scaling, So here's 5 models. We have seen the linear model. It had 2 parameters. In order to store these floats, we need 8 bytes. 4 bytes for each float. Polynomial, 3 parameters, 12 bytes. So you see the pattern here, and the new models are becoming quite large. 1.5 billion parameters reflect to 6 GB of file. A 6 GB of file that will be stored in the location in the storage that will be fetched by the storage initializer. So it will be stored in the disk of the pod, the volume of the pod, to be opened by the model server to copy it in the memory and then copy it in the GPU memory. That's extremely that's an extreme number of copies of the same data set across the different pipeline for deployment. That's just about the deployment. Right. So yeah, here is the disk on the pod that is used by the 2 containers running on that pod to load that model file in between as an intermediate. And to give you some indication, some numbers, I don't know if they are visible, just to do a copy from the bucket to the pod for a 6 GB file takes 90 seconds. That's a long warm-up time for a serverless function, right? And you need another 25 seconds to load this 6 GB file to the GPU memory. Some tricks here is that some people are using NVMe volumes for the disk to make at least the reading faster and the writing when it comes. But the bottleneck in the writing is the I/O with the remote. The bottleneck on the reading can be also the disk. So with NVMe, we speed up this the loading of the CUDA stream synchronize function. And there are some model servers, like Triton from NVIDIA, that offers also an add-on on it called a faster transformer that is optimized to use this function and do the direct copy from the disk to the GPU just by using the CPU memory as a cache and not completely loading the file on the CPU memory and then doing the copy to the GPU memory. The drawback is that this container is 32 GB. We've been looking at the Omni containers earlier, right? And we are struggling to, let's get rid of Docker and use distroless to make my container like 4 megabytes for my Go application. And suddenly the data scientist is coming with 32 GB of container. How do I even put this in production in a serverless function? So here's the story. The language models have been increasing over time because we see the effect in the way that we understand the world, right? The more parameters they have, the more expressive they are, and the better they can define the understanding of the world. So if we take the whole internet, the whole Wikipedia, and put it in a language model, let's also add Stack Overflow and GitHub there, we have a nice model, a nice GPT that can help us code better. And these models now have 1 trillion parameters. 1 trillion parameters reflect to some terabytes. So 175 billion parameters, that is the official GPT-3 size of parameters, is 700 gigabytes. How do we have a model of 700 gigabytes? How do we even load it in GPU? The biggest GPU I know, at least from retail, is like 24 gigabytes. Maybe there are some GPUs in the cloud providers with 40 and 80 gigabytes, but not 700 gigabytes. Here's the first trick, floating point precision. We know FP32 is what we have seen with 8 digits after the dot. Some data scientists like to transform it to FP16. So suddenly, by doing the post-training quantization, my array of floats, which had 8 digits after the dot, suddenly has 4 digits. Yes? So my floating point 16 is much cheaper than floating point 32 because instead of having the need to have 4 bytes for each floating point, I only need to have 2. So suddenly from my 700 gigabytes GPT-3 model is becoming 350. That's a big reduction, but not enough. Yeah, in that experiment, it dropped from 2 megabytes to 1 megabyte because it was a simple couple of millions parameters model. And another trick or another thing that we are doing, and we need the help of the data scientist here, is to, during training, to split the model in different chunks. Because the model itself is not, so the W that has the parameters, it's not just an array of 1 trillion elements. It's an array of arrays, and each array of this big array has the weights of the hidden layer. So maybe we can have each hidden layer stored in a file. And then we can load the one layer in the one GPU and the other layer on another GPU. Because actually when I'm getting the input, I'm multiplying the input with the input layer, and then the output of that, I'm multiplying it with the next hidden layer, etc., etc. So I can afford to have one chunk in the GPU, let me also visualize it here, to have the one chunk in the one GPU and the other chunk in the other GPU. So when I'm doing the matrix multiplication for the first hidden layer, I'm going to the one, and the second, I'm going to the other. And for that, we don't really need a lot of coding. There are nice libraries like Huggingface Accelerate that offer this out-of-the-box capability with 4 lines of code in Python. It's important to maintain, though, the device mapping of which hidden layers are stored in which GPU in order to be able to route the next matrix multiplication request to the appropriate GPU. Of course, there is an overhead on that, and there is an effect on the speed of prediction, but it's something we can deal with if we are building the next large language model system. And yeah, it looks like I'm out of slides. Okay, it's hidden. Unskip. So this is the summary. We have seen some challenges like that are coming from the model size, actually, right? The model size can give a hit on the transfer from the Docker registry to from the container registry to your Kubernetes cluster, the loading time from the disk, the GPU, and we've seen some techniques about deployment monitoring and runtime. I can also do a demo. Maybe that's better. So I have I'm using the K-serve inference service, and the inference service has a predictor and a transformer. And what I'm saying is that, sorry, wrong part. So I have a storage URI with my model location, and I'm defining that I need the 1 GPU in that case. And I'm going to use the Triton model format, and that's the 7 billion parameters model from Bloom. And my transformer will use this tokenizer, and this is enough space to load. If I will do the test with 7 billion parameters model, and I will send the input site reliability engineer helps organizations do what the model is going to do, and output length is equals 5, I'm asking for predicting the next 5 words after this string. So if I will do that, I'm going to get an answer that to improve their performance by reducing. If I'll increase the output length and send the same request, it takes more time because instead of producing 5 next words, it's producing 15 next words. Yes, and that's why you see also this effect in ChatGPT that is slowly building the answer because it's not waiting for the full answer to arrive in order to send you the result of the prediction, but give you each prediction as it's coming. I don't need to. The faster transformer has a little bit better performance. Better performance in terms of response time. We're talking about 200 milliseconds, or no, 100 milliseconds. But it really depends on the output length. If I will just increase this to 20 or 100, asking it to give me a larger story, it will just take longer to complete. Yeah? It took more, like 1 second here. And you can see the answer. But the important part is that this has an effect on the amount of matrix multiplication that is doing in your GPU. For each word, it's doing the tokenization to get the right token, and then to get the input, and then put it in the matrix multiplication with the weights to calculate the next layer and the next layer. And this has an effect on the cost that you spend on GPU time. So serving a large language model is important to do it on GPU. And these are the tricks or the experience I can share with you about doing it. Thank you. Do you have any questions?